All right, so we're finally about to start getting into the process of finding an answer to something. Right now, you guys can use some sizing guidelines and put some stuff on some preliminary drawings, but you still don't know anything about the real design. So from this point on until, so this is lecture 6, structures 1, until lecture 4 of structures 2, you won't have any final answers. So what I've done is broke it down into sections. So this is where I've talked about in structures 1, we're going to find everything about the factored loads. And in structures 2, we're going to work on figuring out what the reduced capacity is. And remember, the entire point is to make sure that the factored load is less than the reduced capacity. So for the rest of this term, we're going to focus on figuring out what those factored loads is. But what we really care about is the factored load internally in our structural elements. So there's a bit of a process to be able to figure that out. First, we have to figure out what the loads are acting on our building. Then we have to figure out how those loads get transferred to the elements we need to design. And then we need to figure out how that transferred load works out to an internal load in our object. And then we will have some factored loads. And at the end of the term, we'll talk about how we illustrate those or show those, because sometimes it's handy to do it graphically as well. Still have to do the math, but sometimes it's handy to be able to do or have a graphical representation of what that looks like. And so from this point on, everything that we do are things that structural engineers do every day. And in fact, you're going to see spreadsheets that I've done little captures of and embedded in the lecture that are just like the ones that I do in my coursework. Not in my coursework, in my actual project design. So you're going to see loading charts for snow and wind and seismic that look just like what I will do for a project. Now, you're going to be seeing one small part of it because you're going to see that for wind we have actually a bunch of different calculations we need to do, and you're going to be looking at one very small element of the calculation. So this is a very simplified version of it, but it's going to help you understand the process and understand what the engineers are talking about when they say this is what we have to worry about. So today we're going to focus on basically what are we talking about when we talk about these loads? Like what do these values mean? Because we're talking about units of measurement that some of you might not be familiar with, so you don't have a real sense of what it means. So I'll try to quantify that for you and give you a sense of what these values mean. Then we're going to talk about live loads, dead loads, and then some of the environmental loads like snow, wind, and earthquake on our buildings. Next week, we'll talk about a few of the less common loads on our buildings, but that still exist and we need to think about. And then we talk about how we combine those loads, because obviously a building doesn't have just a dead load or just a live load. It has a bunch of those together. And I've been talking about that pesky thing of factoring our loads. Next week we'll also talk about what factoring means and what those load factors are for various loads. So you'll often see shorthand. We're engineers and we get lazy writing everything out, and we like to give letter assignments to things. And I know there's only 26 letters in the alphabet, so sometimes you see these letters pop up for different things, and so you have to have an understanding of what the context is. So if we're talking about the loads and you see these letters, this is probably what we're talking about. If you see dead, you're talking about a D, you're talking about a dead load. And that means we'll talk about that in a little bit. We'll talk about what these different loads mean. Live load is an L usually. S is usually given for snow load. W for wind load. Earthquake is an E. Sometimes I'll use a Q, honestly. It depends what mood I'm in. T is often used for temperature. H we can use for soil load sometimes, and P will often be pre-stress. Now, the ones we're going to be looking at the most are these 5 right here. Those are going to be the ones primarily that we talk about. Often these loads are going to be expressed in kilonewtons or kPa, and kPa is kilonewtons per meter squared. And so you'll have to know the context to know which one we're talking about, or look at the units or understand what we're talking about. So I'll try to give you a sense of what a kilonewton and what a kPa means. So a kilonewton is a unit of measurement that we use in the metric system. And just to give you a sense of what it is around, well, it is 224.81 pounds. So if you have a good sense of what pounds are, and as much as we work in a metric system here, we often still talk about weight in the imperial system, so most of us have a sense of what a pound is. Maybe you're from the UK and you talk about it in stone, but you've probably experienced enough in the world to know the sense of what a pound is. You probably know your own personal weight in pounds. I know I do, and we're sadly going to use mine several times throughout the term because it's a handy one to be able to use for some calculations. If we're going to use a person, we might as well use me. So we'll often just round that 224.81 to 225. Just a handy, quick ability to say how many kilonewtons something is. If you know it in pounds, you can change it over to kilonewtons pretty easily. So 1 kilonewton is about 225 pounds. So if you see 5 kilonewtons, it's not as small as you might have the sense of it being. It seems like a small number, but if you're talking about it in pounds, that's quite a large number. So kilonewtons are what we're going to be using for units of measurement of our force. So to give you a sense of a kilonewton, here is Arnold at 225 pounds, which was what he was at a peak weight. So Arnold is a pretty good sense for us of what a kilonewton is. I tried to modernize this. Channing Tatum is like 180 pounds, which seemed shocking to me. I looked up The Rock, and he is more. So it was really hard. It looks like Arnold is the perfect set of visual for 225 pounds. There was someone that I used to work with back in the day, and he was a tall, lanky gentleman who had not an ounce of fat on him, but he was 225 pounds, and we used to call him Kilonewton Corey, because it was just an easy way to refer to exactly what we needed for a kilonewton. I hate using a model. I don't like that. I don't like the sense of what a model means, but it was a really good thing to show half of a kilonewton. There's not many people that actually weigh half a kilonewton. Actually, throughout all of high school and university, that was exactly my weight. It was half a kilonewton. It is not anymore, and I am fine with that. I feel very good about that. But to give you a sense of what half a kilonewton is, it's about 112 pounds. Here is me and 2 hockey pals. You can see I'm no longer half a kilonewton, and they are even more than me. So you can see here are 3 people added up to be 2.44 kilonewtons. Just to kind of give you, I just want to be able to start quickly having you have a visual sense of what that means. Just so you have a feel of, if you see 5 kilonewtons, well, that's probably going to be 5 or 6 hockey players is what you're talking about there. Just to give you that kind of quick reference set, because you don't really have a feel for what it means, and it's hard to talk about something when you don't have a sense of it. So the funner one is, what does 1 kPa mean? What is 1 kPa? Well, a kPa, the units, is actually kilonewton per meter squared. So what we're saying is that is how many kilonewtons on every square meter of area. So if we have Arnold here, and this square is 1 meter by 1 meter, 1 kPa is 1 Arnold on 1 meter by 1 meter squared. So that gives you a good sense. Now, he's technically kind of a point load, so we're more talking about Arnold kind of spread out over that 1 kPa, or that 1 meter by 1 meter squared, so 1 kilonewton over 1 meter by 1 meter squared. But this starts to give you a sense of what we're talking about when we talk about 1 kPa. Just to give you another kind of visual example of it, if we had somebody that weighed half of a kilonewton, to have 1 kPa, we'd need 2 of them over our 1 meter by 1 meter squared. That one person that weighed half a kilonewton over a 1 meter by 1 meter squared is half of a kPa, or 0.5 kPa, just to start to give you this sense. So now we're going to talk about live loads. I like talking about live loads first because we can understand it pretty easily. It's often based on the people and sometimes the things that can easily be moved around within a building. So that would be all of the people and all of the stuff that's not anchored down. So if it's anchored down, it's a dead load. If it's movable, it's a live load. So I have posted for you, and it's in the module, and it's also in the downloads module, just so you can find it easily, a live load table. So really what they've done is they've said, all right, if you have this type of building, this is the live load you can expect to see within the building. And so if you know what type of building you're designing, which is our job because we're the designers, you and me working together are the designers, if you know what building you're designing, you know what live load you need to design that building to hold. So we have it broken down into assembly loads, offices, libraries, corridors, residential, and there's more. And then within assembly, they have different criteria for the assembly loads within that. So an assembly area has 4.8 kPa most of the time as the live load requirement. And you can see that in the table that I posted for you. And it'll say a type of room, here's the live load you need to use. What we're saying with 4.8 kPa is in 1 meter by 1 meter squared, we could have 4.8 Arnolds standing in a 1 meter by 1 meter square area on your floor. So that's tight spacing to have 4.8 Arnolds jammed into that space. And Arnold's got a really tight, his body mass index, there's a lot of weight packed into one small package there. We've got our half a kPa, or a half a kilonewton model. We need 9.6 of that model to give us 4.8 kPa. So that's a lot of people crammed into a 1 meter by 1 meter square. What I used to do at this point, if we were in a room together, I would always, before class, tape on the floor a 1 meter by 1 meter square. And then I would invite some people to come up and stand in the square with me. I would say I was 1 and I'd get 4 more people, making us about 4.8, well, making us about 5 people jammed into the square. And then I'd point out that probably none of us were actually 1 kilonewton. You know, in the class, you probably only have 1 or 2 people that are a kilonewton in weight, maybe more. Depends on your body mass index and your bone structure, all of that kind of stuff. So I'd say, you know what, probably average we're somewhere less than that. So somewhere between 4.8 and 9.6 people is a good representation of 4.8 kPa. So I'd invite 2 more people to give us 7 people jammed in our 1 meter by 1 meter square. And it is tight. It's not comfortable. We actually don't, as people, enjoy being in that space. It's not something we like. Does it happen? Hells yeah. We see it all the time. Here is an image of downtown Toronto during the Raptors parade. Now you can see that every square meter by square meter, or 1 meter by 1 meter square of that space has definitely got more than 7 people in it. So if there is anything in this space that has nothing underneath it, it's not sitting on the ground, if that's a building underneath there, we need to design it to be able to support those loads. And I can tell you, this is a project of ours. Or not, well, it was partly my project back in the day when I worked at Blackwell. If you remember, there are actually images of people climbing up on this. There was pictures of people sitting up here watching the parade go by. So 4.8 kPa is a real design requirement, but we don't like it that much. So there's a few other funny things that I'll talk about in a minute. So other assembly areas, what things fall into assembly areas? Well, bleachers, stadiums, grandstands. Look at this. Here's, since it's Toronto, I'm going to use Toronto, and I'm going to use Toronto being the best for things. Here's back in the day when the Blue Jays won the World Series. And you can see people crammed in here. Again, 4.8 kPa. When might we not have 4.0 kPa in an assembly area? Well, the criteria they say is if it's got fixed seating, the odds are people can't be jammed in quite so tight because the seat literally gets in the way. There is a heavy clause there, and it is stadiums. Because if you've ever been in a stadium when your team is winning, the home team is winning, it is bananas in there. And people will stand on seats and jump around and cram into spots. So fixed seating applies really well for churches and schools, theaters, but stadiums, nuh-uh. People get crazy in stadiums. So for there, they say it doesn't matter if there's fixed seats. People are going to climb on everything. We're still going to use 4.8 kPa. Dining halls, if they are under 100 square meters, we use 2.4 kPa. But if it's over 100 square meters, we say 4.8 kPa. And if you've ever been to a wedding, here's why. They clear those tables out of the dining hall if you can have, if you're over 100 square meters, because it will inevitably turn into a dance floor. I should go back and find an image of me in university when we had our engineering banquet in the professor's fancy dining hall. There are pictures of me with a carafe of wine dancing on the head table. If there is a place to clear out the tables and dance, people will do it. So a non-assembly area, a really good example, might be an office building. Here's the thing though, they say though, even for an office building, ground floor, we're still going to use 4.8 kPa. If you've been in if you've ever been in a high-rise building, you know that that ground floor usually has a lobby and an entrance area where people can gather. I've been at, fancy little hors d'oeuvre things in the lobbies of the big buildings in Toronto because, again, they will be used for a party space if they can be used for a party space. It will happen. So ground floor, 4.8 kPa. Another good reason is if there is a reason to exit the building, you can have everyone from those 2.4 kPa floors coming down onto the lobby floor simultaneously. So you can very easily end up with 4.8 kPa down there. Now here's a thing that has nothing to do with live load, but I'm just going to highlight it right now. We tend to call level 2 the first floor above grade. I know there are different societies around the world that would call this level 1 and this level 0. That's fine. I will try to always talk about floors above grade if I can. So this might be level 1 or level 0, depends how you work on it. But this floor at grade here, here's our column. This column does not support this floor. So our column from level 1 to level 2 supports level 2, level 3, level 4, and the roof. The column from level 2 to level 3 supports level 3, level 4, and the roof. This is important because we're going to do exercises where we figure out the loads on these columns. And I know most people are thinking, why are you explaining this to me? But for somebody that's never actually had the opportunity to think about it, every year, this catches 4 or 5 people up, and they get really frustrated about it. So I just wanted to take the time to explain that right now. This column here, or the column from level 1 to level 2, isn't supporting level 2. It stops at level 2, so it does not have load on it from level 1. So why would we care so much about 4.8 if it's at grade? It's sitting on the ground here, we've got soil here, no big deal. But again, in our big cities, we often have things happening below grade here. There's pathway systems, big basements, so this 4.8 kPa can be a really big deal for anything below grade here. Residential live loads are 1.9 kPa. They used to have a clause in the building code, and this changed in 2012, or the OBC 2012. Bedrooms used to be 1.4 kPa, and all the rest of the building used to be 1.9. So you might still see old documentations. In fact, Dave even the other day was like, what are you talking about? Bedrooms are 1.4 kPa. And I had to point out that changed. He hasn't designed anything. It's all fine. We're good. But that was a code change where they changed it to 1.9 kPa. I don't know what happened in what bedroom that made them decide to change it to 1.9 kPa. Maybe they just got tired of always having to differentiate. But now it's easy. Residents, 1.9 kPa. Vehicles are a live load. And this one is really interesting because it can impact other parts of our design as well. Parking garages, cars are 2.4 kPa. And you're thinking, what the straight up F, Shannon? Live loads for people in an assembly are 4.8 kPa, but a parking garage with cars is only 2.4 kPa. Cars are crazy heavy. And that is true. A car is heavy, but the area that the car is over is actually bigger than the amount it weighs compared to a person or a group of people in a tight space. So the car over an area is 2.4 kPa or less. Now some of you might be saying, but wait a second, what about the tire? The tire is only a really super tiny area. And you're right, that is something that we worry about. But that is a separate calculation from what we're talking about right now. We're just talking about the design of the overall elements here. And we're talking about how much load you can pack into a zone. We do, as engineers, do checks for pressure due to a tire area with the load of the vehicle on it. But that is well beyond what we're talking about for this course, and it usually just has an impact on our decks, the design of the actual decking material itself. So cars, 2.4 kPa. If you're talking about parking garages with buses or light trucks, it's 6 kPa. And parking garages with big trucks is 12 kPa. Now this has a big impact for driveways, sidewalks areas, and basements. Because if a big truck can get into it, like a fire truck, or drive down it, it's 12 kPa. Let's come back and look at this image for a second. If we had remember, if this is grade, and we have a fire truck pull up and park right here, that 12 kPa is really important for whatever we're designing right here. It's also going to be important when we talk about soil loads on foundation walls. And we'll talk about that next week because we talk about a surcharge, or how much weight is outside the building trying to make our soil push into a hole. And this 12 kPa becomes really important in those calculations. Now, let's talk about live load reduction factors. A live load reduction factor says, you know what? We have a zone where people could come and have a party, and we could have 4.8 kPa of people in that zone. We need to design that for 4.8 kPa. So all of those elements that are under that zone definitely need to be designed for 4.8 kPa. But As the area gets bigger and bigger and bigger, the statistical probability of the entire area being jam-packed with people goes down. So each element that has a small area of load needs to be designed for 4.8 kPa, but something like a column that is picking up 5 stories of tributary area, the statistical probability of all of those stories being fully maxed out at 4.8 kPa at the exact same time starts to go down. So we say, yeah, a beam carrying some small tributary area, doesn't matter where it is in this assembly we're talking about, 4.8 kPa. But the column that is picking up a bit of a bunch of areas or a really huge area, it starts to be unlikely that all of that sees the maximum load at the exact same time. So we build that into our calculation, and that's where we use our live load reduction factor. We have 2 different live load reduction factors. We have one for non-assembly areas, and we have one for assembly areas. For a non-assembly area, if our tributary area is less than 20 meters squared, our live load reduction factor is 1. You don't get to do anything. You don't touch your live load. The factor for live load reduction factor is 1. It does not mean your live load goes away. It means that you don't get to reduce it at all. Remember, this is a reduction factor. But in a non-assembly area, if you have more, if your object is holding up more than 20 square meters of area, the odds of that entire area being fully maxed out with load all at once goes down, and you get to use this live load reduction factor. It bottoms out at 30%. So you could have anywhere from 1 or 100% of your live load down to 30% of your live load. And so if you have exactly 20 square meters of area, you're going to have a live load reduction factor of 1, or you're using 100% of your live load. If you have a really large tributary area, you're going to get down pretty close to 30% of your live load. Live load reduction factor for assembly areas. We say that the area is much larger, that we could end up with maximum live load assembly on. So we say anything less than 80 square meters, use the full live load, 100% of the live load. You don't get to use a live load reduction factor. If you have more than 80 meters squared, you get to start to apply this live load reduction factor to your live load. Different elements in your building will have different live load reduction factors because we're talking about an individual element. If we had this building cross-section here, the tributary area that is impacting the design of this beam right here might be 1. I don't know the actual tributary area on that because I just made it up, but it might be 1. Whereas this column over here is picking up half of this entire building. It might have a live load reduction factor getting close to our 50%. So different elements in the building will have different live load reduction factors. In fact, this column right here, the purple one, it's only carrying a much smaller portion of the building than the column was. This is just to kind of give you a sense. The green column was carrying half of the entire building, or probably a quarter because there's a back to it. Whereas the purple one is only carrying, a half of each of those beams. So different elements can have different live load reduction factors. We're going to go through a calculation where we look at a column all the way down through a building and look at the loads on it and what the live load reduction factor is and how it varies throughout the height of the column. So the series of calculations I'm going to do throughout this lecture, I decided to just take one building and use it for all the calculations. It just gives us kind of a reference building that we can use without having to make up 5 new buildings. I can just use the same building throughout our series of calculations. So here's our building. We've got 1, 2, 3, 4, 5, 6 bays here. 1, 2, 3, 4 bays here. There's probably a ground floor, but it's a slab on grade, so we're not worried about that. We've got a level 2, a level 3, a level 4, and a roof. Here it is in plan. Here are our 6 bays that are 7 meters each, and here are 4 bays that are 8 meters each. And here's just an elevation or a section through our building where we've got level 1, which we haven't modeled because if you were an architect, you would have a lot more drawn in here. You probably have a ground floor and a slab. But this was just talking about the bones of the building. These are the shoes. We're not drawing the shoes down here. We're drawing the bones of the building. So we've got level 2, level 3, level 4, and the roof. And so here are the heights of each of those stories. So we've got 4.2 meters here, and then each of these is 3.2 meters high. And here's just the cross section through the other direction. So let's do a column example using a live load reduction factor. So we're going to talk about column 1A. We're going to look at this column right here. So it is going to be picking, so here's our grid line B, and here's our grid line 2, here's our grid line A, and our grid line 1. We're going to have to think about what its tributary area is, and then we're going to have to think about what the loads are on this column and figure out what the load is, the live load is on this column at each floor. So, for whatever reason this says A4, but A1, same thing, just fine. We know it's an office building. They've told us it's an office building. So a ground floor would have 4.8 kPa. And these 3 floors, level 2, 3, and 4, would have 2.4 kPa. The roof, 0. Now, here's the thing. Every year, someone goes in and opens the National Building Code and the OBCC, or the OBC, the Ontario Building Code, and says, Shannon, a roof needs to be designed for 1 kPa live load. And you're right, it does, but it does not have to be in conjunction with the other loads. So that means that our snow load up here on our roof will govern our design. We just need to make sure that if there's nothing else happening, we have to design for 1 kPa. But we don't have to design it in conjunction with anything else. So for you, for all intents and purposes, no live load on the roof if it's inaccessible. If I tell you that people can get up on that roof, you might have a different live load requirement. But I would be very explicit if you had a different live load requirement on the roof that you need to design for. If you're doing a studio project that is accessible, so maybe it's a rooftop restaurant or a garden park, something like that, you will need probably 4.8 kPa. I doubt it's going to be an office up there. It would probably be an assembly area if you're having it up there. So 4.8 kPa. Back in the day when you were allowed to go places in Toronto, if you ever went to the Fifth, it was a rooftop restaurant in downtown Toronto. Or maybe you went to Crocodile Rock back before they tore it down. Those had rooftop patios, 4.8 kPa, even though they were a roof, because they were accessible. So we want to figure out the load, the live load, including any live load reduction factors, from level 4 to the roof, so it's picking up the roof. Level 3 to level 4, level 3 to level 4 is picking up level 4 and the roof. The column from level 2 to level 3 is picking up level 3, level 4, and the roof. And the column from level 1 to level 2 is picking up level 2, level 3, level 4, and the roof. 4.8 kPa doesn't matter to us for what we're going to be calculating here. But I like to show it because I like to be consistent. And all of these things are true. There is 4.8 kPa down here on this floor. It just doesn't happen to be something we need to know for designing this column. But it is a true thing. So I try to get in the habit of showing that to you. So let's go through that calculation now. So let's take a look at this column at all of the levels. We'll start with the easiest one, and we'll go back and forth between these. We'll start with level 4 to roof. So we want to start with our level 4 to roof column. So this one right here. Let's come back and take a look here. This column right here, there's a column here, and it's hard to see, but there's a column here, and here, and here. We're looking at the main plan. If we looked at that 3D ISO, we could see it. So this column here, it's exactly like our table. We've got 4 columns, and you know intuitively, you can't see it, the camera's pointing down, you know that a table with columns here and here and here, that if you have a weight on this, that a quarter of it's going to go to each column. Meaning that this zone here, a quarter of it is going to go to each column. So if we have, maybe it'll let me do this. If this is our entire zone that we're talking about, the column we are concerned about is picking up that portion of tributary area. And intuitively you understand this when you see a table. So that's all we're doing here. So we have an 8-meter bay here and a 7-meter bay here. So we can calculate our tributary area here. So tributary area is going to be 8 meters divided by 2 times 7 meters divided by 2. 8 divided by 2 times 7 divided by 2 gives us 14 meters squared. Now, let's just think for a second. What's the live load on our roof? The live load on our roof is 0. The live load reduction factor only applies to areas that have live load. We actually have 0 meters squared tributary area due to live load on the roof. There is no live load on the roof. So our column from level 4 to the roof has 0 live load and 0 tributary area due to that live load. Let's look at level 3 to level 4. So level 3 to level 4, it is carrying level 3 and the roof. We know that the roof had no tributary area and no live load associated with it. So the tributary area from level 3, well actually let's talk about what the live load is first. They told us it was an office building with 2.4 kPa of live load. The tributary area is 14 meters squared. The tributary area of live load is 14 meters squared. It is picking up 14 meters squared from the roof, but it doesn't have any live load on it, and we are only talking about area that has live load on it when we apply our live load reduction factor. So we have 14 meters squared of live load. Do we get to apply our live load reduction factor? Now, if you guys remember, for a non-assembly load, our live load reduction factor equaled 0.3 plus the square root of 9.8 divided by our tributary area. They just called it A, or area, but you get the idea. But the tributary area had to be greater than 20 meters squared. What does that make our live load reduction factor? It doesn't make it 0. We only have 14 meters squared, and we need at least 20 meters squared to have a live load reduction factor. So what we're really saying is our live load reduction factor equals 1. So our live load is 1 for our live load reduction factor times 2.4 kPa, which if you want, you could write as kilonewtons per meter squared, times 14 meters squared. You can see our meters squared canceled out, and we'll only be left with kilonewtons. 2.4 times 14 equals 33.6. Now we can look at level 2 to level 3. Now level 2 to level 3 supports level 3, level 4, and the roof. Remember, it doesn't support level 2 because it starts at level 2. It goes from level 2 to level 3. So the tributary area for live load on the column from level 2 to level 3 is the tributary area from level 3 and the tributary area from level 4. So tributary area from level 4, we already figured out, was 14 meters squared. The tributary area from level 3, it's the same tributary area on all the floors, 14 meters squared. So our tributary area is 28 meters squared. Our live load is still 2.4 kPa. And we want to know what our live load reduction factor, if we get to make use of one, is. Somebody keeps using my black pens, and they write a lot better than me, and they kill my black pens. There you go. You got a new black pen over there. So we want to know what our live load reduction factor is. We have a tributary area greater than 20 meters squared. We have greater than 20 meters squared because we have 28 meters squared. So we get to make use of this live load reduction factor. And it's 0.3 plus the square root of 9.8 divided by our tributary area, or 28. Live load reduction factor, 0.3 plus the square root 9.8 divided by 28 gives us 0.8916. I'm going to keep a few significant digits just for fun. You probably wouldn't need to keep that many if you were doing this calculation. I've just kept them for fun right now. So the live load on the column between level 2 and level 3, that's picking up live load on level 3 and level 4, is 0.8916 times our 2.4 kPa times our 28 meters squared. And we end up with, I did something funny there. Oh, no I didn't, sorry. So 0.8916 times 2.4 times 28 equals 59.92 kilonewtons. What would it have been if we hadn't used our live load reduction factor? We would have gotten 76.2 kilonewtons. What we're saying here is that the odds of both level 3 and level 4 in that zone having full 2.4 kPa live load is statistically improbable. Maybe they'd be highly loaded, but the odds of them both being fully loaded is low. Let's take a look at our column from level 1 to level 2. So this supports level 2, level 3, level 4, and the roof. But the roof doesn't have any live load on it, so it's just level 2, level 3, and level 4 that have our live load on it. They've all had the same tributary area. So tributary area for level 2 plus level 3 plus level 4. These are all ones that have live load. It's 14 plus 14 plus 14 equals 42 meters squared. Our live load is 2.4 kPa. And our live load reduction factor is 0.3 plus the square root of 9.8 divided by 42. Remember, as the area gets bigger, the statistical probability of it being fully loaded goes down, which means we should get a lower live load reduction factor. 0.3 plus the square root of 9.8 divided by 42. Oh, I forgot a bracket there. 0.3 plus the square root of 9.8 divided by 42 equals 0.7830. And let's figure out what our live load is. So 0.7830 times 42 times 2.4. We get 78.93 kilonewtons. Let's see what that load would have been if we hadn't used the live load reduction factor. It would have been 42 times 2.4, or 100.8 kilonewtons. So the live load reduction factor just means it's statistically unlikely that we'd be actually able to see that much load on that column all at once, because the odds of people being there are pretty low. I've worked this out for you and shown it a slightly different way if it's helpful, so you can see all of the columns here. I've worked it out in a table here where I've actually shown you the tributary area due to live load, the live load reduction factor, the load without the live load reduction factor, and then the load with the live load reduction factor at each of the floors. Remembering that it's supporting the floors above as we go through this. So dead loads are all of the things that make up the building itself. So it's not just the weight of the structure, but the things that are permanently attached to the building. So the structure might be the steel columns and the steel beams and the concrete on metal deck, for example, but the grout that we put down and then the tile that we put on top of that, wall cladding systems, all of those things will be part of the dead loads. In fact, we include mechanical and electrical in that as well. In a house, you'd have gypsum wallboard or your drywall, plywood that you don't need structurally, but maybe you need to be able to apply something to, brick veneer. All of those things would be part of the dead loads in the building. We break it out into two categories. For us, you don't give two hoots about this difference. For you, it's all just dead loads. But you maybe will hear the engineers talking about it if they talk about self-weight and superimposed dead loads. And so what we're talking about is the self-weight of the structural elements and sometimes the superimposed elements as a separate thing. One of the reasons that's handy for me as the engineer, and again, not a difference to you, you guys are just going to talk about it all as dead loads together. But what I will often do in my model is keep the self-weights held back, and I'm modeling something because I might be changing around what the elements are, and I'll let the program that's helping me design it actually apply the self-weight to the system. That said, on a set of drawings, we'll have to show what all the weights we used in our assumptions for designing the building. Now, assumptions. What a pain in the butt, because again, it implies that you guys have to just pick numbers at random. That's not the case. The same way we had with live loads, we have tables and charts that tell us what these things weigh, because if you're building concrete on metal deck, you're not the first person to do it, and we know how much these systems weigh. So we can look these things up. So let's take a look at what some of these might be. So here we have a dead load table that I have supplied for you guys again on Quercus. So you can access all of these. Each of the different material codes, so right here I've got my steel code, and I've got my wood code, and I've got my concrete code, my masonry codes back over there. We don't use it quite as often. I have a glass one, the glass one's small. Fabric, that one's a lot harder. It's usually proprietor supplied. But books and books and books for these things. But each one of these major material ones has a table like this. This one is from the steel book, and I find it the handiest, and it's the one we're going to reference the most often. So if I ask you to look something up, I can tell you I'm lazy. Every single one's going to be from this page. All the dead loads I'm going to give you are going to be from this page. You can figure everything out from this page. You might have to do the teeniest, tiniest, most simplest calculation, but it will be all on this page, only because sometimes they give it in 100 millimeters thick, and we want 50 millimeters or 150 millimeters. That's the maximum of the calculations you're going to have to do for this. And some addition. What I would like to do is go through the dead loads without flipping my camera down like I did for the live load, and I'm going to try to write directly on the screen. Sometimes it makes my computer crap out, and I have to restart everything. So we'll see. If that starts to be a problem, I'll stop and do it, kind of looking down at a hand calculation. But if this works, we'll go through it this way. I will also open up, my computer has gone and changed things for me. I'm going to open up for you while we do this the dead load tables. That's not what this is. This is a duct passing underneath a grade beam. That is not anything that concerns you. Let me just open up the dead loads for you guys here. All right. So just so I have it handily and quickly so that we can reference it very easily, this is the same table that you were seeing in your lecture slides. So we can see it here. We can just zoom in a little bit closer because it's really hard for me to zoom in on the slideshow. So let's come back to our slideshow here. We want to know what the dead load of a roof assembly is. So they've told us that we have 4-ply roofing tile or roofing with gravel, 6 inches of rigid glass fiber insulation, 38 metal deck, open web steel joists, the structural steel, mechanical, electrical, and a suspended ceiling. And we want to know what the total load for this is. So what we can do is I will start pulling these things off from the PDF that I showed you, and I'll try writing it here without making my my computer go haywire on me. If it doesn't work, I have other ways we can go through it. So the very first thing that it said was roofing. We have 4-ply with gravel. So let's come over here to roofing and zoom in. Roofing, 4-ply, no gravel, but we had 4-ply with gravel. So 4-ply asphalt and gravel. 0.32, and it looks like everything in this is in kPa. So let's see if my pen, I know for you guys it mostly looks like you get to see up my nose when I lean forward like this. All right, it's working. So 0.32 kPa. So we've got our weight for our roofing. The next thing is 6 inches of rigid glass fiber insulation. Now, 6 inches is close to 150 millimeters. Or if you want to get very specific, 6 times 25.4. Oh, that's just weird. You're just seeing a weird reflection of me. Ah, there we are. 6 times 25.4 is 152.4 millimeters. So let's take a look at this. Oh, there's a whole section just on insulation, but look, it says per 100 millimeters thick. So we have 152 millimeters, so we'll need to multiply this by 1.5 or 1.52. We had glass fiber rigid insulation. So 100 millimeters or 4 inches weighs 0.07 kPa. We have 6 inches or 152 millimeters. We're going to have 0.107 kPa. So we had We have 0.07 times 152 divided by 100, because we're just making a ratio there. We want 1.52 times what the weight they tell us for 100 millimeters. And we get, let's round it, 0.11 kPa. I can tell you that for anything that you have to do in Quarkus, because how many digits we put in is very, very, very important, because Quarkus is a pain in the ass. But it does let me put a tiny range. So as much as I say it has to be exact, if you made a small rounding error here or you kept this, I build that buffer into the calculation. And I look at what are all the reasonable ranges. What if you had used 150 here instead of 100? Because sometimes we'll refer to 6 inches as 150 millimeters. I go through and make that check. So I do it all the different ways that are possibly right to see what the range of answers is, to make sure no one gets penalized for something simple like that. But for here, we've got our 6 inches of rigid glass fiber insulation is 0.11 kPa. 38 metal deck. Let's look up our 38 metal deck. So 38 metal deck. There is a whole section of steel decks here. And look at this. Steel decks, 38 millimeters deep. They have 2 different numbers. I am going to tell you that the norm is this, the 0.91 millimeters thick. If it wasn't this, I would tell you and you would know. So for you guys, this is the norm, unless I tell you something differently. So it looks like for us, we need to use, my mouse is not happy with this because I see it over here as well. Where did you go? We will use 0.1 kPa for the weight of the deck. So let's come back to our slide here. So 0.1 kPa. Now, open web steel joists. This one you guys need to know a little bit more about how these buildings get built. I can tell you that what we do as engineers, we figure out what the weight of our steel is, and then we imagine we crumple it into a ball, because remember, these things are localized. And we're talking about the area we're using, or the load we're using to design our floor. So what we pretend to do is take the weight of all our steel for the floor, or all of our open web steel joists for the floor, crumple them into a ball, melt them down, and spread them like peanut butter all over the floor. Obviously, that's not what we actually do, but it's how we imagine this load being. You do not have to stop and figure out the actual weight of your open web steel joists and your steel beams, and then allocate it in that particular spot. If I'm using software, I might do that. But for a general calculation for dead load assembly like this, it is not what we would do. And in fact, you don't even know enough to know what a reasonable open web steel joist and steel weight is. So I would give that to you. So this is something that I would give to you in any situation. And now I can't remember what I used in this one, and because I'm using both screens, I can't see ahead to know what I used in this example. So I'm just going to pull this up on my phone so that I can see it easily without sliding ahead a little bit. Now, remember, this is coming from years of experience. It is based on knowing a little bit about the building, and if it's kind of a heavier design or a lighter design, and knowing what is a reasonable load to assume for the steel. And what the engineers would do is make this assumption, and then once the building is fully designed, go back and check and see if they used a reasonable assumption for the weights of their open web steel joists and their steel. And if we've done that, then we say, great, we're not going to redesign anything. If we didn't use a heavy enough load, we might have to go back and redo our design here. So this is something that I give you. So we're going to assume 0.15 kPa for the open web steel joists, and 0.2 kPa for the steel. So we only have two things left in our assembly now, and normally I would often take the time to draw this out and show this assembly, but you're going to see that I've done that in the worked out example for you. Mechanical, electrical, and suspended. So let's go and look at our chart here. My Zoom isn't working. Oh, today is one of those days. Okay, so I have no idea what's happening here and why I can't make a thing that I've done a gazillion times work. Maybe if I close it, it'll just love me when I open it back up. Sorry guys. These are the blurbs that happen when you're, this could happen if we were teaching live too, so you would all just have to bear with me and roll your eyes. It is trying to open itself back up. Let's see, okay, we've got it back open. Let's open our dead load table. There we go. That was a weird blurb that my mouse wouldn't zoom in. Okay, so what we need now is mechanical electrical allowance and a suspended ceiling load. Again, some of this comes from experience, but it is here in the chart. So look at this, ceilings, because this is what we're talking about. Some of these things were on top of our deck, and some of these things are hanging below our deck. So look at this. Ducts, pipes, wiring allowance, average condition, 0.25. You'll often see engineering drawings just refer to this as MAC-ELEC, or mechanical and electrical allowance. And so that's taking in all the things you might hang from the underside of your structure. There's another one here, tiled ceiling and suspension system with fixtures, average. That is a suspended ceiling. Your average, crappy, white tile with T-bars and wires hanging down from your whatever's supporting it, suspended ceiling system. And these are probably two of the most common systems or weights that we would need in our dead loads. They're pretty common in assembly systems. So our assembly system has, we just know that we need a mechanical and electrical allowance because they don't even tell us what's in there. We just know we need an allowance. And then for our suspended ceiling, we have 0.2 kPa. So 0.25 for the mechanical electrical and 0.2 for the suspended ceiling. Now, if we were doing a laboratory or a water treatment plant or a communication hub, this is probably not enough. If this is the average condition and we're doing something outside of average mechanical electrical systems, we probably need to stop and think about what those weights would need to be. And so in those situations, there are kind of standards for those types of buildings that need to be looked at. So I've done a few of those where we actually increase that allowance. So let's go back to our table here. So mechanical, electrical. .25 kPa. Suspended 0.2 kPa. So now we can add these up and figure out what our load is for our roof? What design load, what dead design load do we need for our roof? So we have 0.32 plus 0.11 Actually, it looks like when I did this, I used 150 millimeters and rounded down. So just to be consistent with the rest of the notes, we're going to use the 0.1 there. So 0.32 plus 0.1 plus 0.1 plus 0.15 plus 0.2 plus 0.25 plus 0.2 equals 1.32 kPa. So we have a dead load for our roof. We've now been able to figure out what the dead load we need to design all the elements on our roof for. Now this is where understanding assemblies becomes very important. We have our steel beam or our open web steel, well actually we have a steel beam that holds up an open web steel joist, that holds up metal deck, that has the roofing and insulation on top of it. So all of those things are supporting themselves and the hierarchy above it, as well as the roof and the insulation. The mechanical and electrical doesn't often get hung from the metal deck. It often gets hung from the underside of the open web steel joists. And same with the suspended ceilings. So the open web steel joists carry the mechanical, electrical, and suspended and the deck, but the deck doesn't carry the open web steel joists or the mechanical or electrical or the suspended. So if we were talking about the design of the deck itself, 1.32 kPa seems a bit high because it's sitting on the open web steel joists, which is sitting on the steel. So this seems like overkill. And so what we'll often do in our design, and you're not going to have to do this, but I want you to understand that it is a thought process that engineers think about. We will look at the sub-layers of the structure and how much load they're holding. So I'll often even stop and think about what things are supporting what. So the deck, definitely supporting the roofing and the insulation and itself. But it isn't supporting the open web steel joists. It sits on top of the open web steel joist. The open web steel joist supports it. It's like me. I'm sitting on my chair, so the chair is supporting me, but I'm not supporting the chair. So the weight of me wouldn't need to include the chair, but the chair would need to include the weight of me. Same thing here. So our deck is supporting the 0.32 for the roofing, the 0.1 for the rigid insulation, and the 0.1 for itself. Or 0.52 kPa. The open web steel joists are carrying everything that the deck was carrying and themselves, and mechanical and electrical can be suspended from the joists, as can the suspended ceiling. But the steel is supporting the open web steel joists. The open web steel joist is not supporting the steel. So it looks like our open web steel joists need to be designed for the load of everything except the steel. So we have 1.32 minus 0.2, or the weight of the steel. So the open web steel joists are carrying 1.12 kPa. Again, this isn't something I'm going to make you do much of. But I do want you to be aware that we think about this, because if we're like stuck on just a certain thing or something is a little bit over, knowing this might help you just a little bit. Again, not too much concern for you for this course, but it's something you should know that we do as a process. So here that is all worked out for you. And you can see here I've got the same kind of tagging of these things. Let's look at the floor of our building. Here they're saying we've got carpet, we've got 38 deck, but it's supporting 64 concrete, open web steel joists, steel, mechanical, electrical, and suspended. Well, some of this we've already done and we already know. So let's write in the things that we've already looked up because they're not going to change. That table hasn't changed just because we're talking about a new floor. So we know mechanical and electrical, we assume 0.25 kPa, and that a suspended ceiling is often 0.2 kPa. For our steel, we're going to assume 0.2 kPa. And for our open web steel joists, we're going to assume 0.15 kPa. So we really only have to look up our carpet and our 64 concrete on 38 deck. So let's go look up those two right now. Floor finishes, carpeting, 0.1 kPa. That seems kind of easy. Let's come over here to our steel decks. Well, they've got 38 metal deck here and a weight of concrete, but I told you that that concrete, the profile, concrete on metal deck, oh, didn't like that. Is it gonna make it zoom funny again? So how do you know how much area there is of concrete? That doesn't seem very fair. And like that you'd have to calculate that out each time when we use concrete on metal deck all the time. Oh, it did it again. Well, look at this. Deck slabs. 38 millimeter deck with 65 millimeters of normal density, ND, normal density, cover. Well, 1.95 kPa. It looks like they've already done it for us. So our carpet, 0.1 kPa, 38 metal deck with 60, we always say 64, but 65 millimeter normal density concrete, 1.95 kPa. Let's go back to our summation here. So we've got the weight of all of our assembly for our floors. We can add these up. So we've got 0.1 plus 1.95 plus 0.15 plus 0.2 plus 0.25 plus 0.2. We've got 2.85 kPa. Great. Let's do the same thing that we did and just break out what our decking assembly is supporting and what our joists are supporting. In case we needed to design those, we can make use of the lighter loads for designing them because they're not supporting the things that support them. So let's pull out all the things that the deck supports. it looks like that's it. It supports itself and the carpet. The deck sits on the open web steel joists, the joist sits on the steel, and then the mechanical, electrical, and the suspended hang from the open web steel joists. So we've got .05 kPa for the deck. The open web steel joists, the deck, the carpet, their own self-weight, mechanical, electrical, and suspended. The only thing they're not supporting is the steel, because the steel holds them up. So we end up with being able to design the open web steel joists for .65 kPa. Sorry if I don't talk while I'm writing because it seems to make a lag happen between the video, so I'm not just, it's not that I can't talk while I'm writing, it's that I don't want it to make it garbled or have you guys lose consistency in the flow of the communication. So here is the dead loads for our floors. So now we know what our live loads are, we know what our dead load for the roof, and we know what the dead load for the floors is. So here it is, just written a little bit cleaner if you want to be able to take a look at it. This one I did not break out, so we'll go through and look these ones up. We also have, so you can have a kPa over the floor. Remember, it's a 1 meter by 1 meter section. So you could have a 1 meter by 1 meter section of wall. You could have wind blow on it, but you could also have how much it weighs downward. So 1 meter by 1 meter of this wall weighs how many kilonewtons? And that's a thing that we can calculate. So they've said that our wall assembly is 19 millimeters of gypsum wallboard, 38 by 89 stud, 4 inches of rigid fiberglass insulation, 19 millimeters of plywood, and ½ inch of stone veneer. So let's go look up what all of these are. Let's go to our, oh, I forgot that it made it not work. Maybe I just need to open up this one thing and it'll work. No. Look at this. It's working now, but not as that. So it'll work when I have it as the hand, which is slightly annoying because you don't know what I'm pointing at. Okay, so the first thing was 19 millimeters of gypsum wallboard, or JWB, drywall is what we're talking about. They have it in a few spots. They have it in the roofing spot, and they have it in the walls and cladding spot, because we can use it in either space. The weight is the same. So see here, they've got gypsum wallboard per 10 millimeters, weighs 0.08 kPa. We have 19 millimeters of it, or we need 1.9 times 0.08, or 0.08 times 19 divided by 10 gives us 0.152, or 0.15 kPa for our gypsum wallboard. The next thing is 38 by 89 stud. Well look, 38 by 89 wood studs, at 400 millimeters center on center. We talked about what's normal is about 16 inches center to center for these sort of things. Looks like this is a normal sort of thing. So 38 by 89 wood studs weighs 0.05 kPa. Looks like we've got the second thing. The next thing they wanted was 4 inches of glass fiber rigid insulation. So let's come over to our insulation. Glass fiber rigid per 100 millimeters thick. 4 inches is 100 millimeters. I mean, it's 102 millimeters, but they're talking about 4 inches here. 0.07. 19 millimeters of plywood now. Well, they have a whole section for plywood, 19 millimeters thick plywood, 0.11. And then the last thing was 1/2 inch of stone veneer. Walls and cladding. Stone veneer per 25 millimeters, which is an inch. So we want 1/2 inch or half of 0.4 kPa. Or if you wanted to say it this way, 0.4 times 12.5 divided by 25, 0.2, or half of 0.4 is 0.2. So let's come back to our listing. All right, we saw all of these, we pulled all of these out, and the total is 0.58 kPa. So every 1 meter by 1 meter of wall is going to weigh 0.58 kilonewtons, acting downwards. So we can have an area with a load pushing on it, or we can have an area with a load acting down on it. Both of those things can be true. And this is a question that I have on the assignment that throws everybody off every year, but it's really important because we use it when we calculate the weights of our walls. So here those are worked out, and you can see I've drawn these assemblies for you, just to give you a sense of how these things go together. You can see that the metal deck sits on our open web steel joist, which sits on our steel beam. Same thing over here. And then here's just a quick look at our wall assembly. All right, the next topic we're going to talk about is climatic data, or the things acting on our building from outside. Up till now, we've been picking what the loads are. I mean, we're picking what type of building we're making, so we're picking the live loads that go in it. I mean, our client is ultimately making that choice, but that's coming from us. We are choosing the assembly, so we're technically in control of these dead loads. The environmental, or the climatic loads, are a little bit different. They need to be prescribed in the building code, but then they need to have allowances made for location and type of building and the things happening around it. And so they build that in a few different ways. One of the other things they do with the climatic data is they say we're going to apply an importance factor. Basically, how important is your building to people? And this sounds funny because you would say, well, why wouldn't we just design everything to the maximum capacity? And the answer is money. What we're talking about is probable risk. Everything is about risk and probable risk. We don't design a house to withstand a tornado in southern Ontario because we have 2 buildings a year destroyed by tornadoes. And even those usually aren't fully destroyed. They usually have siding torn off of them, for example. It is not a real risk in southern Ontario that we would design our buildings for a direct hit by a tornado. Now, having been in my cottage this summer when a tornado hit, I can tell you that it is the most terrifying friggin' thing in the entire world. But again, our cottage stood up. We had rain coming sideways through our shut windows. It was wild. It was intense. We had trees fall down all around us. It was the most terrifying 30 seconds of my entire life. And then it was done and gone, and the sun came back out. So it is not a real risk. What we do is we say certain buildings need to have certain functionality should a disaster happen. My cottage just needed to be standing after a tornado hit. Now, tornado is a bit an extreme example because we don't often usually design for the loads of tornadoes. But it did not have to function at its best capacity after the tornado hit. In fact, we had no power for days afterwards. The kids weren't with us. We went up there to work because we were writing a book, and we went up there for a dedicated week to work at the cottage. Instead, we ended up chopping up trees for days, but we didn't have to have full functionality of our building afterwards. We just needed it to be safe. So here are the categories that they give for buildings. They give low, normal, high, and post-disaster. If you know nothing else, your building is a normal building, and the factor is 1. That is just your building. Your factor, your importance factor is 1. I will tell you if it's something different. For whatever reason, every year in studio projects and on the exam, people decide to make their building a high importance or post-disaster, and I cannot fathom why, especially when I stand here and say, don't do it unless I tell you to. And I am telling you not to unless I tell you to. So, importance factor is going to be normal. Your building is going to be a normal building. Low means that if your building collapsed, no one could get hurt. So it's pretty hard to make that claim. I have done it for a few art pieces where, if a hurricane hits and you're standing beside an art piece, that's probably on you. Maybe you should be inside a building that is of normal importance. It's rare that I would apply a low importance factor. Normal is normal. It is the majority of the time what we do. A high importance factor would be where we need our building to not function after a disaster, but we need it to be a safe space for people to gather after a disaster. I always think of Hurricane Katrina, where people went to the stadium. Turns out the stadium didn't fare well in the hurricane either. So that is a situation where we just needed cover. We needed safety. Often in dire storms, people gather in a community center if their building doesn't make it through the disaster. But we don't expect people to go skating or play volleyball. So we don't need full functionality of that building. We don't need it to operate as it's intended post-disaster. A post-disaster building means we want that building to survive the apocalypse. We want it to function as it was meant to function with no blip even after our disaster. So post-disaster, we want it to maintain full functionality. So the things that need that level of design, police stations, ambulance hubs, hospitals for sure, communication hubs. So I have little brick buildings that needed to be designed for post-disaster because we rely so heavily on communication now. Prisons need to be designed as post-disaster. Anything that needs to maintain full functionality post-disaster. I'm not sure what project you guys will be doing in your studio project next year. And I'm not sure what you're doing right now, but it's not a comprehensive studio, so it's less important. They change the building every year, so I don't know what you guys are going to be doing next year. Normally it's next term, so I kind of have an idea of what's coming. But you guys could end up with a community center, which would be high importance. You could end up with a theater, which would not. It would be normal importance. So these are things where you, as the designer, have to understand the use of your building when applying the importance factor. Here are the factors that we use once we've made that decision. So here's where I'm going to bring up another thing. Ultimate limit states, or ULS, serviceability limit states, SLS. I'm going to drive you nuts tracking these two differences for everything from this point on, and you're not going to make any use of it until Lecture 4 of Structures 2. So you're going to be like, Shannon, why the heck are you making us calculate this when we're not going to do anything with this SLS value? But you need to know how to calculate it, and now is the time to learn how to calculate it, but we're going to need it, and it's going to be very important by the time we do Lecture 4 in Structures 2. So bear with me. From this point on, we're going to be calculating an ultimate limit states load, and a serviceability limit states load. Ultimate limit states is all about strength, and serviceability limit states is all about deflection and serviceability. Ultimately, whatever we calculate using this, we will be comparing to our allowable deflection. Everything we calculate using this, we will be comparing to a reduced capacity. So you can see here, for wind, snow, and seismic, for an ultimate limit states, a regular building, the importance factor is 1, which is normal, which means we're not doing anything. It doesn't change our load in any way. For a high importance or a post-disaster importance, our loads start to go up. You can see for a post-disaster building, we design it for 50% more seismic load. So take the worst earthquake your region could possibly see in a certain time frame, and then we multiply it by 50%. Serviceability, look, it stays the same no matter whether it's low, regular, high, or post-disaster. And for wind, we take 3/4 of the load, and for snow, we take 90% of the load. Seismic, we don't worry, or we don't change our serviceability limit states. We don't really do much of a serviceability limit states check for seismic. There is one brief one, and we just use the normal load. So let's talk about our first climatic data load case, and that's snow. Snow is the kind of the one people can get their head around the easiest. So S, I said earlier, snow load. Sometimes you might see me write SL because I'm saying snow load. Snow. IS is the snow importance factor. And remember, we're going to have SLS and ULS, snow importance factor. SS, CB, CW, CS, CA, and SR are things I'm going to explain to you. So let's start looking at what those are. If you feel like it, there's a design resource here, an online design resource. Feel free to check it out if you want anything to help back up your calculations. So SS and SR are things we look up in the building code. They have said that a bunch of engineers have gotten together with a bunch of meteorologists, and they've studied weather patterns and snowfall accumulations, and they've said in each region, here is the probable snowfall for a 1 in 50 year snowfall event. So every 50 years we have an estimated maximum snowfall, and that's what we design to. Now, you can have 2 1 in 50 year snowfall events in the same year. It can happen. Statistically, it's highly unlikely, but it is not a zero chance. So with statistics, it is all about range. And so what we're saying is that this is the statistical probability of your maximum snowfall in this 50-year time frame. Toronto has had a 1 in 50 year snowstorm since I've lived here, which has been 18 years. So, we get these things more often than every 50 years. Or we might go 100 years without it. My cottage hopefully withstood a 1 in 200 year windstorm during that tornado. Okay, so ground snow load with a 1 in 50 year probability of occurrence in a year, based on measured depths and densities for locations in Canada. I've pulled out it because we're in Toronto. It's the one I'm pulling up for you to look at. I just realized I have to address something for Structures 2 because they're doing their project in New York, which makes it a little bit harder because we're talking about Canadian codes. Not something you guys have to worry about right now. But I've pulled out, because the university is based in Toronto, we're going to talk about things based in Toronto. Every code is slightly different, but they're all similar. We're talking about the Canadian code, so we're going to design to the Canadian code. So we have Toronto Metropolitan Region, broken out into Etobicoke, North York, Scarborough, and Toronto City Hall. I want to remind a note for myself, for my Structures 2 students. because they're supposed to look this up for their project, and it's been that way for time out of time, and now all of a sudden it's in New York, so we have to figure out a way around that. Okay, so Etobicoke, North York, Scarborough, Toronto City Hall. Snow load in kPa for a 1 in 50 year probability. We have SS and SR. SR is your snow rain association. So this is a wetness that might happen with your snow cover. This is not the same thing as a rain load. A rain load is something different. So SR is basically how much weight might be sucked up in your snow, essentially, to make it wet. I don't know what day you guys are watching this, but today, here in Port Hope, we had probably 8 to 10 centimeters of snow, and now it's raining on top of it. So that moisture is sticking into the snow. So these are both things that we look up. So this is the ground snowfall, and this is the wetness that kind of goes with it. And then we have some factors that we apply. CB is the basic snow load factor. We are doing a Part 4 building. There is such a thing as Part 9 of our building code, which is for wood frame, small scale construction. They get to use 0.6. We're not designing to that. There is still inevitably somebody that will use 0.6 when they're doing their calculations. Don't. Use 0.8 for our basic snow load factor. What they're saying there is the snow falls down on the ground and we accumulate this much. If your building is of normal size, when the snow falls, a little bit tends to fall off of it. And so we reduce the amount that would normally fall on the ground if it's falling on the building. So if this is how much would fall on the ground, some little bit blows off and, kind of disturbance falls on it. So for you, it's 0.8. I have done a few very large buildings where at the center of the building, you don't get to use 0.8 just because it's so massive. And that was a community center that was 1 floor, and it had 3 skating rinks and 3 pools in it. So you can imagine a very large surface area that the snow in the middle couldn't possibly go off the edge. But 0.8 is the norm. CW is the exposure factor. Look at this. You're going to use 1. I don't think I have ever asked my students to use anything but 1 because it is so impossible to use. I've never been able to make it work. I haven't designed any projects in the prairies, but what this is saying is that if your building is fully exposed on all sides, wind can blow the snow off your roof. The criteria means that you can have nothing, you have to have nothing close to your building for 1 kilometer all the way around it. We cannot achieve that. It's just, I have trees around my house. There's other buildings in a city. It is really hard to achieve that. Again, what happens if you did use it and then they build a building next door within your kilometer radius with nothing around it? So you guys are going to be using 1 for your exposure factor on your snow load. CS is your slope factor. Now, this says that if you have a flat roof, you use your full snow load. As you start to tilt your roof up, and this is the angle here that we're talking about, when you get to 30 degrees, you get to start to account for snow sliding off your roof. Up to 30 degrees, you keep the same snow load. At 30 degrees, it starts to reduce until you go up to 70 degrees, and then it says all the snow will have come off your roof. So anything higher than that, you don't have to worry about. Now, in Toronto, you don't see a lot of really steep pitched roofs. A lot of architects will be like, this is going to save the world. We're going to steeply pitch our roof and get rid of all of the snow that's on it. Well, in actuality, the snow loads in southern Ontario aren't that high. We don't benefit that much from it because we still have all the weight of the material. Now you've got an increased zone for wind blowing on it. It ends up being more materials, more zone to heat. So economically, it is not You wouldn't do an A-frame or a steeply pitched roof in Toronto to save your snow load. You might have other reasons to do that style of roof, but that's not a reason to do it. Don't make that your reason to do it. There are places where it might be a reason to do it. You guys probably all know the classic style of onion dome Russian architecture. That was for snow load. You know, it would slide off the top and then slide off the sides. So that was motivated for it. There is one more factor, and it is the accumulation factor, and it is very, very, very important, but it is very, very, very complicated to calculate, which means I can't reasonably make you do it in this course. But it is heavily important that you know it exists. So, you can see here, you don't need to calculate it, you're going to use 1 as your accumulation factor. The accumulation factor is due to higher buildings or objects on your roof. When it's not 1, we're calculating the ASL, or the accumulated snow load factor. Here's just an example of what it looks like. You are, again, not going to have to calculate this. But I want you to know it exists because it can have a massive impact on the design. So let's take a look. This is a building that we're building. We've got a high part here, a low part here, a mechanical pop-up here, and a parapet here. The snow falls and it all looks like this. And this would be perfect, except we know that there is some wind blowing, snow moves around, you see it all the time. We can end up with accumulations here due to the higher roof, accumulations here because we have a pop-up, and accumulations here because of this parapet on the side. You can see the massive increase in snow here. I am doing a project in Huntsville right now, and the basic snow load on the roof is 2.7 kPa. The canopy, which has a high roof above it, ends up with 7.5 kPa of snow load on the canopy. That is an insanely massive amount of snow. And it, as you can imagine, very much governs the design of that canopy. So it is something that is very important that you know about, but I'm not going to make you calculate it. You're going to use 1 as your snow load accumulation factor, not 0. When I say don't worry about it, it doesn't make it 0, because if you use 0, you're going to wipe out your snow load equation. You're going to use 1 when I say you don't have to worry about it. Oh, so I need to fix this. We have a 42 meter by 32 meter, right? We had 7 times 6 and 8 times 4, yeah. So we have a 42 meter by 32 meter building. This is that building that I showed you in the earlier when we were talking about our just before our live loads. Find the snow loading on the roof in kPa for both an importance factor for ULS and SLS. What is the snow load on the roof in kPa for importance factor of ULS if the building was high importance? Just as an exercise, we want to see what that means if it was a high importance factor. It shouldn't be. They've said it's a regular importance factor, but maybe there's talk about changing its designation for some reason. Maybe they want to make it community housing at some point, to make it a shelter. So maybe the client wants to know the impact of that change. And then what is the total load on the roof of the building in kilonewtons? The third question is not a thing we normally calculate, but I want you to see the magnitude of the weight of the snow. Remembering that 1 kilonewton is 225 pounds. So this is just to help us get our head around how much snow that is. So let's go through and do that calculation. All right, so for our snow load, we know that they want us to figure out what the snow load is in kPa for both our serviceability and our strength design. They also want us to calculate it for high importance in case they change the designation to high importance. And then they wanted us to find the total force in kilonewtons, even though that's not a thing we would normally calculate for a building. It's just to give you a sense of how much load that is. So let's take a look at the snow load calculations. So snow load, we know that the equation is our importance factor for snow times our SS, which is multiplied by CB, CW, CS, CA, plus SR. Well, for our importance factor, if it is regular, IULS is 1, and ISLS is 0.9. I gave you that chart, and it's in the slideshow that shows you those. If it's high importance, our importance factor for strength is 1.15, but our serviceability importance factor doesn't change. Remember, the ULS is about life safety. The 0.9 is about preserving your finishes. All right, SS and SR. SS and SR, let's take a look. They said it was in Toronto. Let's go back and look at that chart for Toronto here. SS for Toronto downtown is 0.9, and SR is 0.4. So that's easy. That's something we can look up. 0.9 kPa and 0.4 kPa. So we've got most of our equation. These we know are factors that get applied to it. CB, I've told you you are using 0.8. CW is the wind exposure factor, which you can manage to make something else, but it's really hard, and I have actually never really done it for snow load, so we're going to use 1. CS is the slope factor. That does get used a lot, and depending on your type of roof, you would be able to make good use of that. The building we're doing has a flat roof, so we know that we don't have any slope, which means we don't get any reduction in the snow load. And then our snow accumulation factor, or our ASL factor, we know is very, very important, but what we're talking about is the overall building here, and I've told you you don't have to calculate it. It seems crazy that there'd be no mechanical units on this building's roof, but we're going with that. They have them protected in the basement, let's say. So we're going to use an accumulation factor of 1. So it looks like we can calculate our snow load for ULS. Let's talk about our regular importance here. Our snow load for strength would be 1 times, and then in the brackets, 0.9 times more brackets. And I'm going to tell you the bracket placement in this is the thing people screw up the most. People get confused by this being multiplied by SS and then SR being added over here. They'll often lump this all in, or they'll multiply these and add this and then multiply it by SS. So pay attention to your brackets here, people. So we have 0.8 times 1 times 1 times 1 plus our SR, and we can calculate this as 1 times bracket 0.9 times bracket 0.8 times 1 times 1 times 1, end bracket, plus 0.4, end bracket. And we get 1.12 kPa. So that's our strength version of it. Let's look at our serviceability value. Well, 0.9 times, well, our SS doesn't change. Our CB doesn't change. Our CW, our CS, and our CA doesn't change. And our SR doesn't change. So it looks like the only thing that changed was 0.9. Or 0.9 times 0.9 times 0.8 times 1 times 1 times 1. 1.01 kPa. Let's also calculate our high importance version of this, because they asked us to do both. So everything stays the same. The only thing that changes here is our importance factor. That, ladies and gentlemen, was the sigh of ultimate stress coming from beside me. Things are tense with deadlines in this house at the moment. So we have 1.15 times 0.9 times 0.8 times 1 times 1 times 1. We have 1.29 kPa. Look at this though. For our serviceability, everything stays the same as here. So it's 0.9 times 0.9 times 0.8 times 1 times 1 times 1 plus 0.4. I'm not plugging it into my calculator again because we just did it there. 1.01 kPa. They also asked us to figure out what the total loads were. The tributary area of the building was, we had 6 bays of 7 meters times 4 bays of 8 meters. So 6 times 7 equals 42, and 4 times 8 equals 32. 42 times 32 equals 1,344 meters squared. So they asked us to figure out what the total snow load was for all of these conditions. So let's do total snow load ULS equals 1.12 times 1,344. 1.12 times 1,344 gives us 1,505 kilonewtons. So for that office building, that seems pretty normal in size. Remember, gold ring, so this is 42 by 32. Gold ring, it was a 54 meter span plus the end bays. It was something like 65 meters by 35 meters, I think, something along that lines. So a big building, but not a behemoth of a building. We have on the roof of that, not even counting accumulated snow loads, it's the same as 1,505 Arnolds having a party up on the roof. So the snow load can really accumulate to be a large load on your building. And let's take a look what that would be for SLS. Again, these total loads aren't something we would normally calculate for for buildings, but I want to do it to show you a sense of what these values are. So for our serviceability, it's 1,357. 1.01 times 1344. Yeah, so I have an Excel version of this where the rounding of that snow load carried over to make like 2 kilonewtons difference. So for anything for you guys in the assignments and exams, I would go through all the possibilities of rounding, whether you kept tight significant digits or not, or I'd be explicit about what amount of significant digits to keep throughout the process. And so just to be thorough here, for the high importance version of the building, we would have 1.29 times 1,344. And then this would be the same. 1.29 times 1,344. Or 1,734 kilonewtons. So you can see that we increase the amount of load on the building by making it high importance. So let's just come back here to the worked out calculation. So here you have it worked out. There's some small rounding differences in my values, and that's because of rounding in these, where I rounded this to 1.29, but it actually calculates out to 1.28 something. So those are why we have slight differences of like 2 kilonewtons in these answers, but it's just about rounding. So there's another thing that you won't need to calculate, but you need to know that it exists, because it's very important. As much as I'm going to say it rarely governs. It's a thing that the building department needs to know you've thought about, and in places like Florida, I would imagine it would be the governing load on a roof. We just happen to be talking more about Southern Ontario, where it tends not to govern. But I can't let you walk away from your desks not knowing these other things exist. So it's important that you know it exists and why and when it might govern. So the rain load is not SR. This is a separate thing that you are not going to have to calculate. So see, I've said it right here. You won't need to calculate this. All roofs must be designed to support the 24-hour rainfall. Some roofs may be required to support more due to the nature of the drains or the locations of the overflow scuppers. So that would be in communication between the design team and the engineer and the mechanical engineer, because that usually comes from the mechanical engineer, what type of whether using control flow drains. So you might have drains that basically stifle the flow of rain down the drains to prevent it from clogging other things. So in that situation...
Sorry. Sorry, got a delivery in a minute.
Those are boxes of wine. COVID, you order in bulk. So we have to know how much rain is going to fall out there. Now, most of the time we have scuppers or drains that just need to retain 24 hours of rainfall. What we say is 24 hours in case the drains get clogged. Over that, you would expect someone to go up onto the roof and manually unclog the drains. So, hurricane hits, you don't want somebody up on the roof trying to unclog the drains, but after the hurricane, they can get up there and unclog the drains. So, this is just again for reference, but I wanted to show you this. I want to go back here for a second, and let's just look at that snow chart here. Take a look at this. Etobicoke and Toronto City Hall, 1 day rain 1 in 50 year storm. So this is the 24-hour rainfall. Etobicoke, 108 millimeters. Toronto City Hall, 97 millimeters. Now, I don't know how many of you live locally to here, but I think it was 2013 where we had a massive rain system park over specifically Etobicoke and the western side of Toronto. And in an hour, they got 127 millimeters of rain. So far exceeded the 1 in 50 year 24-hour rainfall event in 1 hour. So part of that is due to climate change. Part of that is due to that was a statistical anomaly. That was literally the outlier of our 1 in 50 year storm. And so again, remember, this is all about statistics and statistical probability. There was very little structural damage from that 1 in 50 year rainfall. At the time, we were working on Gold Ring, and they hadn't yet finished installing all of the sump equipment, that pumps the water out, and they had just installed their massive, very expensive, like $2 million mechanical system, and the entire basement got flooded. No one in it, no one using it. It was exactly a construction site and meant to be that way. Except it was like the 3 days that it could have possibly happened. And they had just poured the topping over that mechanical unit, so they couldn't lift it back out and replace it. They had to manually take it in piecemeal to replace that mechanical unit. So, worst case timing for something like that because of a statistical anomaly. That said, this is still, I don't think they've bumped it up in the latest code either. They might. We're seeing much more drastic changes in our weather pattern systems. So I would expect that the next several codes are going to see increases in many of these things. So let's just zip forward again back to that rainfall. Okay, so here is why we need to think about rainfall. So all roofs must be designed for the 24-hour rainfall. It only tends to govern if there are large slopes to a drain in the middle of the roof. So when I say not govern, I'm talking about here, because our snow tends to govern. So here's a roof. We get this volume of rain. So that's the total 24-hour volume of rain. It was based on 97 millimeters, and we have that area that it's falling on. If we, now I've dramatized this slope, but if our drain is here, this same volume of rain falls over that projected area no matter what. But see here, the total volume is the same, but the depth of the water at this low point is much deeper, meaning right here, we have a much higher load. So locally, we could see, with steep slopes, regions of roof that are going to be governed by rainfall. In all the projects I've done, I'd say 3 or 4 projects have had 4 or 5 beams governed by the rainfall event. Had to check it, had to think about it, had to do a quick study on it, and that's where I needed to communicate with the architect, because I needed to know where are the drains, what are your slopes. So I needed that layout of drain patterns, and so very early on, the architect needed to think about what type of drains are we using? Do we have scuppers? Where are they going to be, at least roughly, so that we could do a design exercise to find out if there's any elements governed by the rainfall, which there wouldn't normally be because our snow would govern. So we have 2 more major loads that we need to talk about, wind load and seismic load. And I apologize, this is one of the longest lectures that you guys have this term. I know you find it a bit overwhelming. There's 1 or 2 more that are long, but they're at least kind of rhythmic, and people that find it easy can zip forward a bit, and the people that need it, the information's there. This one, I know can drag a little bit, but it's very important that we go through all these steps. If we have to go over 3 hours, I very much apologize, but the advantage is that you can pause it and come back to it. It always was a real struggle when we were doing this live in class because we'd get to the end, I was trying to rush and talk really fast to kind of get through the entire program of the class in the 3-hour segment. So we've had lots of classes where we were shorter than 3 hours. We might have one where we go over, and it could be this one. And I can hear my children melting down, so I can tell you that I'm not exactly enthusiastic to rush this lecture, because if I go past 4:30, can you jump in and take over when Jackie has to leave? You're a prince. So, wind, building. A lot more that we have to think about, because there's all kinds of basically situations and combinations of things we need to think about with wind load. So with the building as a whole, when the wind blows, we have the wind blowing on this side of the building. But as the wind goes around the building, it does some funny things. As it goes over, it actually tries to lift the roof off the building. And then on the far side, it creates basically a dead zone where we get suction, or the leeward side. So as much as the wind is all blowing in this direction, it pulls on this side and sucks on that side. So we have two things that we have to worry about: windward, leeward. We have to worry about suction on the roof. And then we have elements. So that's the building as a whole, so as an object. But you're going to see, well, have you ever stood outside and you're like, it's a lovely day, and you can see the trees blowing off in the distance, and all of a sudden there's a big gust and the tree moves around, but you don't feel it yet, and then the tree stops moving and the wind hits you. The wind isn't even all at once. What we do for a building, there might be spots where there are those gusts hitting it, but it's kind of averaged out over the bigness of the building, if you want to think about it that way. But a single window in that building is like you standing there when that gust hits you. So that window needs to be designed for that singular gust on just it. So we have the building as a whole, and then we have exterior elements of the building that have wind on it. But the inside of buildings have wind pressures as well, so we have to worry about those too. So the basic building wind pressure equation looks like this. Instead of a W here, which would make sense, we write P for pressure. Q is the 1 in 50-year reference wind pressure. So similar to what our SS was in our snow load calculation. IW is our importance factor for wind, and remember, we're going to have a ULS and an SLS version of that. CE is the exposure factor, CP is the pressure coefficient, and CG is the gust factor. That is the part I was talking about where you can see the tree move over there and you're not, and then the tree stops moving and you feel the wind. So that's spread out a little bit over the building as a whole, so a lower gust factor, versus an individual element which has a higher gust factor. So the 1 in 50-year reference wind pressure comes from, and you don't have to calculate this. In fact, I'm going to add that for you, slide 43. It comes from a constant based on air temperature and pressure, and the square of the reference wind velocity in kilometers per hour. You guys are used to hearing wind talked about in kilometers per hour. We don't actually calculate Q because somebody has done this for us again and again and again, where we go and look up what Q is. That said, in the States, they do two things different than us. They use a wind reference velocity, so they'll talk about it in kilometers per hour. So it's not a straight exchange. You can't look something up in the American code and use our code. You would have to convert it. But then there's a second thing that's different. We use a 1 hour gust, an hourly mean. So ours is the hourly mean wind pressure. So we say, okay, this is a pressure, and over an hour of a big storm, this is the average. We have other factors. That's where we use the gust factor to kind of help out those local gusts on it. The states use it's a 3 second, right? They use the 3 second kilometer per hour value. So even if you take their velocity and convert it to Q, it's still not the same thing, because our Q is a 1 hour mean, and theirs, after we've converted kilometers per hour to a pressure, it's a 3 second gust. So there's more that needs to happen, and it can be done, but it's not a straight conversion. So that's just something to be prepared for if you're working back and forth between Canadian and American things. But again, you don't have to calculate this. We're going to look Q up. Here is that exact same chart we just looked at for our snow load. So here was our SS, and here was our SR, and here is our 1 day rainfall, and oh look, hourly wind pressure. 1 in 50 year storm right here. So we vary from 0.44 to 0.47 for our wind pressure that we would use, and then we would modify it based on our building circumstances. So this is placing us in the world. This is the wind pressure placing us in the world. But the same way we had to with snow, we have to take into account localized conditions based on our building. What type of building we're building, what does it look like, what does that do to these values? So we have CE, which is our exposure factor. Open means that there is nothing sheltering our building. Remember for our snow load, I said assume nothing shelters your building? Well, for wind, I'm telling you, for snow, I said assume your building's sheltered. For wind, I'm telling you assume your building is not sheltered. And we assume those two things simultaneously, which I know sounds crazy. But what happens if you assume there's something sheltering your building and they tear it down? There was a street in the core of downtown Toronto that had a series of row houses. The type you're used to seeing that are side by side by side by side that you see kind of all over the place in Toronto. But this was in like the core of downtown Toronto. And they had torn down all the other row houses except for one. And it was a tiny, narrow, long building, and that was all that was left. And it had originally been sharing out its wind load coming from the side with like 15 other buildings, and now by itself it was standing there completely isolated. It was like the Duke of Argyll was the pub that was in it. That pub closed in like 2004, so, and they tore that building down in like what, 2010 I think, something like that. So the point though is that it can happen. It is not, as much as we're talking about long-term life for these buildings, it is not a static thing, and the environment around them can change. So unless you have a super darn good reason, and you would have to convince me otherwise, assume that everything around your building could be torn down and you'd have full wind exposure buffeting this building. So that is your exposure factor, and look, it's based on height. So it's the height divided by 10 to the 0.2. But it has to be at least 0.9. So we don't go lower than 0.9. If your building's only this high, doesn't matter, 0.9. If it's a building for ants, we're still going to use 0.9. I don't know if any of you have ever read Ken Follett's Pillars of the Earth, but in that, they build a grand cathedral. And the big trouble they had building tall is that the buildings kept falling down. And they couldn't figure it out why all of a sudden the buildings would fall down. They reinforced the way they thought they should. And in the book, supposedly, the key character in the building notices walking up around the top of the building that the wind pressure seems higher up there. And that's where we build in this CE, this exposure factor, that as the wind is along the ground, it's kind of dampened a little bit. It kind of stops the wind pressure. It slows it down a little bit. But as you get up high, you don't have that effect. And the wind pressure can be higher as you go up the building. So a high rise, you can end up with like 1.4 high on a building. If your building is perched on the top of a big hill, you would have to treat it like it was that far off the ground. Because this is kind of like lifting your building up off the ground. So there are exposure clauses for tops of cliffs and big hills, for example. CG, this is that gust factor I was talking about. Now, in 50% of the buildings we design in Canada, we break our design code into two things, high-rise and low-rise. In the low-rise category, we treat our building, or our CP-CG factor, as one factor, and they've mushed them together for us. It's defined as the ratio of the maximum effect of the load to the mean effect of the load. Yeah, whatever. Basically the ratio of the peak to the average. It reflects random wind gusts acting for short durations over the structure, fluctuating pressures in the wake of the structure, and fluctuating forces induced by the motion of the structure itself due to the wind. CG, if you weren't combining it with CP, varies from 1 to 2.5. If I'm doing a high-rise building, it's often 2. If I'm doing art pieces, because they're small things, they're more likely to have their entire surface see that peak gust load simultaneously. I'll use 2.5. For you guys, though, you're mostly going to be pulling it out of a table that talks about CP and CG combined together. Now, it is mandated that I make you do these wind load calculations. I think it's silly for you to do these wind load calculations because there are so many clauses within it that it is a bit overwhelming for you guys. So I've made it as a participation mark at the end of this assignment. We're going to go through one so we can tell accreditation that I showed you one. You have at your disposal to do one, but I would not make you do one at that intensity level in the exam by any means. I might make you do a small component of it where it would be very easy to calculate in a few minutes. I would not make you do a 30-minute wind calculation exercise. CP, like I said, for the ones we're going to be doing is often combined with CG, but here's what it would be if you were breaking it out. So this is often if we have a high-rise building, and the code has changed recently. It used to be that almost all the buildings were low-rise. Even Gold Ring, the 5-story building, when I started designing it, the code switched halfway through, and it was a low-rise building according to the old code. The new code came out just before we issued for permit, and it bumped it into a high-rise category. It had a change, but not much, and we redesigned it for that. But many of the buildings that I would have treated as a low-rise building now need to be classified as a high-rise. I had a small laneway house that I was designing recently, and the architect and the builder were so mad at me because the wind stipulations were so intense because of this new clause change that made a laneway house classified as a high-rise. And because now the definition of high-rise has to do with your ratio to your height to your shallowest dimension. So you can imagine a 4-story house that's really narrow is now considered a high-rise building. So that came into play in that project. So in a high-rise, here's how you calculate CP, but we're not going to have to do it because we're going to be using the low-rise classification. So this is the diagram I'm going to show you in the next slide that applies to low buildings. So I showed you this here, what kind of makes it meet a low-rise classification. Sorry. Here is the diagram. Again, this is another thing that gives people a bit of a heart attack because it's a confusing looking diagram. You can see that these values change depending on roof slope. We're going to do a roof slope of 0, so 0 to 5. I'm not going to make you worry about any more than that. We're going to do this shallow roof slope for our wind calculations. This gives us 8 different wind zones. You can see we've got this side, the roof, this side of the roof, and the leeward side. So we're assuming the wind is coming from this direction. So the wind is going like this. This is our windward side. This is our windward side of the roof, our leeward side of the roof, and the leeward side of the building that we can't see. What they've also done is built in a calculation that helps us think about the possibility of our building twisting. So imagine the wind is higher at one end than the other. This isn't about having high wind loads at each end. It's about trying to look at the possibility of our building twisting a little bit. So we have an end zone. So our windward end zone, our roof windward end zone, our roof leeward end zone, and our leeward end zone. So now we have 8 different zones that have a different CP-CG factor. I know. There's a lot of acronyms here. We're going to go through a calculation, but you have all the reference material here to come back and look at. Here's the other thing. All of these arrows are the assumed direction of the wind. If a number is negative, it means that the arrow is drawn wrong. Now this is a technique that is used a lot in engineering, that we assume all things point in one direction and a negative value tells us otherwise. So let's take a look here. I said we're going to use a 0 roof slope. 1 is our windward side of our wall, the main part of our wall. 0.75. It's not a negative number, so it looks like our arrow is right. It is pointing in that direction. Come over here to 4, which is the backside, or the leeward wall portion, is minus 0.55. So the arrow is pointing in this direction, but that negative means it's actually going in that direction. So both the windward and the leeward side are making the building move in the same direction. Now, we're going to be doing flat roofs, and we're not going to be doing the calculation for wind roof suction. So we're really just going to be worrying about the end zone of our windward side, the main zone of our windward side, the end zone of our leeward side, and the main zone of our leeward side. And we're going to go through and do a calculation on the building with that in a minute. Here are all the clauses on how we calculate that. How do we know how big an end zone is? Well, that's a good question. The end zone with y should be the greater of 6 meters or 2z, where z is the width of the gable wall end zone defined below. It's 10% of the least horizontal dimension, 40% of the height, but not less than 4% of the least horizontal dimension, or 1 meter. I know. I will go through one of these with you and calculate it out. Again, for no points do you ever have to do one of these, but I've given you one with worked out solutions should you choose to accept this mission. What other wind calculations do we need to worry about? Or, not you worry about, that I have to worry about, but you should know exist. We have building element wind pressure. So this could be your wall itself. We have wind coming from the outside, and then if we have windows open and things like that, there's wind suctioning on this side. So there's the exterior pressures and the interior pressures acting on that wall. This isn't the building as a whole. This is an element that we're designing now. So we use the same reference wind pressure, the same importance factor, the same CE, but now CP and CG need to be determined, and CPI and CGI, that should be a C. So slide 53, it's supposed to be CGI, not GGI, is the internal gust factor. So those are the internal values that we would look at. So we can calculate the exterior CPCG from this diagram. You're not going to have to do it. Here's roof uplift. And then interior CPI and CGI are like exterior pressures, except we look up CPI and CG, and they give us these here depending on what type of building we have. Basically, it's saying that if you have no operable windows, you're going to have very little internal wind pressure. If you have big operable windows or hangar bay doors, you're going to have lots of internal wind pressure. If any of you have ever been in a condo with an elevator, you know that on a windy day, you can hear that elevator move and you can even still feel like doors move around. We also have mechanical wind pressures that we might have to worry about. So often we'll have negative space pressurized zones to extract air in a particular zone or to deal with heating. We might pressurize a zone of a building. If you have air-inflated fabric structures, those are constantly under pressure to inflate the roof. So those would vary based on specific conditions, but often 0.24 kPa. So we have to think about all of these different pressures when we're designing our elements. Again, you're not going to have to do a calculation for designing an element, but you should know that these all exist. So let's take our building, and again, this is 42 meters by 32 meters by 13 tall. And we want to find the windward and leeward wind load in the regular zones and the end zones in kPa. So we want to find that for regular importance, or for ultimate limit states and serviceability limit states. So we have a regular importance building. And then what is the total wind load in kilonewton for the building in each direction? Now, in snow load, when we did this, I said that's not something we actually calculate. It was just to help give you a sense of the total snow, like the weight of this thing. But for wind load, we actually do calculate this for buildings, and we put it right on the structural drawings. Page 1, we say, here's how much wind load is pushing on our building. We'll do it for wind and earthquake, and we do it so that we can compare, and the building department can see at a glance which one is our governing load case, and that we've thought about it, whether it's wind or seismic, that is kind of our predominant load case. We could have situations where in one direction it's wind and in the other direction it's seismic. So let's go through and do that calculation now. Okay, so now the behemoth of a wind calculation. Again, you have a calculation like this to do that is at a small, well, no, it's almost the same scale, but you don't have to do it for points. It's for you to go through and explore and practice with. Any testing on this would be less intense than this. I can promise you that. I acknowledge that there's a lot in this, so I'm trying to make it as kind of accessible to you as possible. So, wind load. I did just see another thing I need to fix. Okay, so wind load. Let's start by writing out the equation for wind load that I've shown you. So wind load equals the importance factor for wind times the 1 in 50 reference pressure, CE, which is an exposure factor, a pressure factor, and a gust factor. So this one's relatively easy. We probably need to know a few things about our building. So we need to know the width, which we know is 4 bays with 8 meters, or 32 meters. The length is 6 bays of 7 meters, or 42 meters. And the height they gave us is 13.8 meters. We need to know our importance factors. It's a regular importance building. In the snow example, they got us to check both, but it must have freaked them out, and they said, no, let's just stick with a regular importance building. Not that we have a choice in it, but we're going to make sure we don't design a building that needs a high importance designation. So they're not going to turn it into a community center. They're going to keep it as something that only needs a regular importance designation. So that means that for wind, our importance factor for strength is 1. And our serviceability is 0.75. So we only use 3/4 of the wind for serviceability calculations. Q, or our 1 in 50 wind pressure, they gave us as 0.44 kPa. And when I say they, that came from that same table we looked at for snow. So you can see here, Toronto, hourly wind pressure, 0.44. So we have IW and we have Q. CE is the first one that we need to use. CE, I told you, was an equation of H divided by 10 to the 0.2. Well, we have H, so we can go ahead and calculate CE, but we also knew that it had to be greater than 0.9. So let's just see what CE is. We have 13.8 divided by 10 to the power of 0.2. 13.8 divided by 10 gives us 1.067. And it is greater than 0.9, so that seems great. We're ready to go there. We need to meet we need to know if we're doing a high-rise or a low-rise building for CPCG. So is the building low? Is it low? Again, you're not going to have to worry about this. I'm only going to give you low-rise questions. This never even used to be something that I needed to worry about, but H needs to be less than 20 meters. Well, H equals 13.8. We're good. H needs to be less than 0.5 times W, or the smallest dimension building. So we have 0.5 times 32, or 0.5 times 32 equals 16 meters. H equals 13.8. So we do have both of these. We get to use the low importance category. Not low importance, it's a low building. It's not a high rise. So that means the only thing left to figure out is our CP and our CG. And we know for that a low-rise building, CP and CG are smushed together with a little table for us. So let's go take a look at that little table. Here we go. We know that we have a flat-roofed building, and we're not worried about the roof section. So we care about the end zones and the side walls, so zone 1E, 1, 4E, and 4, or our windward and our leeward side of our walls for our end zone and our regular zone. So let's pull those out. So that's these values here. So 1 is 0.75, 1E is 1.15, 4 and 4E are both negative, which means they actually go in the opposite direction of what the arrows show. So the entire building is trying to move in the same direction. And we have 0.55 and 0.8. So let's come back to, So let's write out our CP/CG for windward regular zone, windward end zone, leeward regular zone, and leeward end zone. We pulled these right off of that table. So we have our 0.75, our 1.15, 0.55, and 0.8. Do you notice that I'm not writing the negatives? It's just because I have determined from that image that they're all going in the same direction. So I'm not going to worry about that right now. Now we need to figure out what our end zone length is. End zone was from that list of what we need to figure out is this dimension right here. And that is listed in this chart here. So the end zone width should be the greater of 6m or 2z, where z is determined down here. The lesser of 10% of the least horizontal dimension and 40% of the height, but not less than 4% of the least horizontal dimension, or 1 meter. I usually figure them all out and go from there, so let's figure those all out. So we have 10% min L or W. Well, W is less than L, and we want 10% of that. So 0.1 times 32 equals 3.2 meters. The other one was 40% of H, or 0.4 times 13.8 equals 5.52 meters. So we need the lesser of these two. So it's not this, it's this, but they said, so this is for determining y, we're determining z right here. But they also said it has to be at least 4% min L or W, so 0.04 of 32, so 1.28 seems to be irrelevant. Oh, but yeah, not less than, or 1 meter. So it seems like 3.2 is our Z value, but then we need to use that to figure out Y. I know, this is a pain, I get it. So that figured out Z for us, so we've determined Z, and now the end zone Y is the greater of 6 meters or 2Z. So Y is either 2Z, or 2 times 3.2 equals 6.4 meters, or 6 meters. It's got to be the greater of those two. So 6 meters, 6.4 meters is greater than 6 meters. Looks like 6.4 is our end zone. Let's figure out what the actual wind pressure is in each of our zones here. So I probably could have done this down here a little bit. Let's figure out actually what the wind load is in kPa for each of these zones. Remember that the wind load is
IW, Q150, CE, CP, CG. So for our windward regular zone, we have 1.0 times 0.44 times our CE, which we calculated as 1.067, times CPCG, which is 0.75. So let's calculate that out. We get 0.44 times 1.067 times 0.75. We get 0.35 kPa. Let's do that for all of these, where the only thing that's changing is our CPCG. So 1 stays the same, 0.44 stays the same, 1.067 stays the same. So we can do this for all of these. We can calculate these, and it's 0.54, 0.26, and 0.38. That's me just plugging into the calculator this same equation, changing CPCG for each of these zones. So now here's the hard part. I'm going to draw us a little building. That looks like this. We know that this side is 42 meters, and this side is 32 meters. We know the height is 13.8 meters. So this is a plan. And we've got an end zone here of 6.4 meters. And we've got an end zone here of 6.4 meters. I can get this a bit closer for you guys. I'm messing it up too much. Dave, you have to go relieve Jackie. It's 4:30. I'm really sorry. Thank you. Thank you, thank you, thank you, thank you. So we've got wind going in this direction, where this is our windward side regular zone, and this is our windward side end zone. We also have, this is going to drive you nuts, and I'm going to draw my arrows going this way. And this is our leeward side regular zone, and our leeward side end zone. And we've calculated these. All we need to do now is figure out the area, or the surface area, that these are blowing on. So the windward regular side is blowing on this distance times the height. The windward end zone is blowing on this distance times the height. And we've calculated what these values are. This was 0.35 kPa. This was 0.54 kPa. This is 0.26 kPa. And this is 0.38 kPa. So now it's just simple math of pressure on an area. In the other direction, it's the exact same thing. Bye, Jackie. Self-portrait, that he did. Okay. Thank you, Jackie. So we have to do the same thing going in the other direction, where we have our end zone windward, or 0.54, and we have our windward regular zone of 0.35, and these ones, all of these arrows go in this direction. So this is 0.38, and this is 0.26. And we want to figure out the total load on this building for each of these directions. We've already built our importance factor, our 1 in 50 year reference pressure, and our CE and our CPCG into all of these. Now it's just about figuring out the total areas of these. So let's add those up. So let's look at the long direction. We have our windward regular zone, which is, so we want our total wind load here. We've got 0.35 kPa times 42 meters minus 6.4 meters, because that's that distance there. This is only over this distance, times the height of 13.8 meters, plus 0.54 times 6.4 times also the height, plus 0.26 is the pressure, times 42 meters minus 6.4, or this length right here, plus 0.38 times times 13.8, plus 0.38 times 6.4 times 13.8. So we can plug that all into our calculator here, or I'm actually going to calculate 42 minus 6.4 is, I'm going to calculate that as 35.6 here. All right, I've got 0.35 times 35.6 plus 0.54 times 6.4 plus 0.26 times 35.6 plus 0.38 times 6.4 times my height, 13.8. I end up with a total load of 381.46 kilonewtons. So that is the total wind load in this direction. And I guess you would say in that direction as well, because it would be the same thing. We would have to do the same thing with the end zone being over here, but again, the total value doesn't change. It might change how we model it. Everything okay?
Yeah.
Okay. So let's take a look at the short direction. What do you think? Looking at this side versus this side, do you think this is going to have more or less load? Well, it's a shorter surface area, so I'm going to guess less load. So, short direction. So we want the total wind load. I am going to do this one right now, where we have 32 minus 6.4 is 25.6 meters right here. So we have 0.35 times 25.6 plus 0.54 times 6.4 plus 0.26 times 25.6 plus 0.38 times 6.4 times 13.8 meters tall. If I plug all this in, let's go through it. We've got 0.35 times 25.6 plus 0.54 times 6.4 plus 0.26 times 25.6 plus 0.38 times 6.4 times 13.8 meters tall, and we get 296.8 kilonewtons. Now you're going to find that I have slightly different answers posted simply because I used Excel, which even though it doesn't show the rounding, it doesn't round. It remembers all of it takes infinite digits when you do formulas in Excel. So it will round slightly differently. Again, I always try to build both into any calculations for you guys. So here are our base shears for our building in our strength loads. We have to worry about 381 kilonewtons in this direction and like 297 kilonewtons in this direction.
Okay, take a breath. That was a lot. Let's talk about seismic loads now. I am not going to make you do the big, long, complicated seismic calculation, mostly because a lot of engineers don't even understand where the heck the calculation comes from. It used to be a relatively simplified calculation that was done, and it's very logical why we do it. Everything that we do now is built on that, but as you make it more and more complex, it gets a little bit harder to just intuitively understand. So I'm going to explain both the old method, and I'm going to quickly show you the new method, but I'm going to show you the calculation you're going to do is based on the old method we used to do like pre-2000. And I'm going to take an example and do both for you, and you'll see the difference in the calculation that works out between them. So basically what we're saying with seismic design is that the ground is moving, and it's kind of undulating a little bit. And we're taking our building, and it's moving along this ground. That's a little bit hard to kind of get our head around. So we imagine that our building and the ground is staying still, and we think about how that ground is moving and the angular motion of it, and take the weight of the building and apply it as a force laterally. So almost like your building was tipping on its side. In fact, Dave and I had a problem recently on a project where a type of software where seismic design was acting up. So we literally took the building and tipped it on its side to be able to figure out kind of an approximation of where the flaw in the program was running. It's a program that wasn't meant for what it was doing, so we were kind of forcing it to do it that way. So what we do is, as you can imagine, depending on the earthquake, the more your building's going to move around. And it builds acceleration into it. So there's all kinds of things that build into this. If we're going to take it as a lateral load, dependent on our weight, the amount of that would change depending on where you are. So just to give you a sense, in Toronto, it's about 10% of the gravity weight that we use as a lateral load. Now, let's just read what I've written here. Translate energy-induced movement due to ground movement into a base shear. So we're taking the ground movement and turning it into a force that's trying to slide our building. The base shear in each region can be quantified as a percentage of the dead load and a quarter of the snow load on the building. Because it would be crazy to assume that we're getting our 1 in 50-year snowstorm at the same time we're getting the worst earthquake we could imagine in our region. We might have a snowstorm and an earthquake at the same time, but the odds of them being the worst we could see, the statistical probability of that is absolutely off the chart. We then take that force and distribute it over the building. And so we take it and we apply it as a ratio as we go up further from the ground. So we say more of it is up here than down here, and then we also will figure it out as a moment. The thing that matters for you is that we are taking a percentage of our gravity load and applying it as a lateral load. And we care about, you care about that entire base shear, or what is the force that the building is trying to side against the ground as. So that's what you're going to calculate. Remember in our wind load, we figured out what the total shear of our building is? Well, that's what we're going to do for our earthquake as well. So we're going to use the same building we used throughout the lecture. We're going to use the same dead loads that we calculated. We're going to use the snow load that we calculated to determine the earthquake force in kilonewtons on the building, assuming a typical Toronto building has about 10% of the weight translated into a lateral load. So we're going to use 10% of the weight as a lateral load. So let's go through that now.
Okay, last example, our earthquake example, and my kids are starting to lose their straight up selves at the moment. So I apologize if you hear screaming from any of the four of us at the moment. All right, so we have, so we have the same building, and we wanted to know what earthquake load to use using 10% of weight translated into lateral load. So we have to know the total weight of everything in the building, plus they get us to use 1/4 of the snow load, assuming that the roof might have snow load on it when this earthquake hits. So I usually try to write myself out a little list of all of the loads. What's wrong, Malcolm? Everyone okay? I'm sorry, everyone.
Mama,
Yeah, buddy.
I'm not sitting here a lot of time.
Oh, buddy, come here. I know. So, no, you can't. Well, let me see them. Okay, so tell Duncan that's not nice and to not hit. But I also know sometimes you're a bit of an instigator, and maybe something was going on
I
previous
see
to
my
that.
face.
Yes, you see your face.
Why is it going up to yellow?
Boys,
Daddy has.
Hi.
Yeah, you're going outside, but Mommy's recording a lecture, so can you follow Daddy? Mommy is working. Everybody is very happy to see you. It's all right. It's okay. I love you, Duncan. Ouch. Okay. I really love you too, buddy. Okay, that's just a little bit of the usual. Sorry. So our quake load, we're almost done. We're getting to the end. This is a very long lecture, and I'm very, very sorry about it. So we need to figure out the load on all of our floors. We don't have to worry about live load because people kind of move to balance a seismic load here. So let's write out our load type here. Let's write out the value of it here, the area that it's on, and the total load. Make that in kilonewtons, that in meters squared. This is the kPa value we're talking about. So roof, dead load. we calculated that. If we go back to our earlier calculations, we calculated that the dead load on the roof is 1.32 kPa. So every 1 meter by 1 meter zone of that roof has 1.32 kilonewtons on it. We also know that the area of the roof is 1,344 meters squared. So that means we can figure out what the total load in kilonewtons is. It's 1,774 kilonewtons. Level 4 dead. We also calculated that by looking at the assembly, and we know that it's 2.85 kPa. We did that. We looked at the assembly and added up all the loads and calculated 2.85. The area of level 4 stays the same, as it's the same dimensions on all the floors. So 2.85 times 1,344, we get 3,830 kilonewtons. Level 3 dead, well, all of the floors had the same dead load. And they all had the same area. So their total loads in kilonewtons would stay the same. We don't use level 1 in calculating quake because level 1 is where we actually transfer the loads back into the soil. The building is being thrown around, but we actually put the load back into the soil. As it's moving with the building, the ground floors are just going along for the ride. It's the upper floors that are trying to move relative to the ground floor. We have two other things we need to worry about. We have roof, snow. So our snow load, it's 1/4 of our actual snow load. We calculated a snow load of 1.12. So we only have to use 1.28 kPa of snow, meaning that only 1/4 of that snow load will be up on the roof in the event that this massive earthquake hits. So we have 0.28 times 1,344, or 376 kilonewtons. We also have all the walls. The walls are heavy too, so we have to worry about that. So we calculated what our wall load was, and we know that our wall load is 0.58 kPa. The total area is all of the walls around our building, or 42 meters times 13.8, and we have 2 of those sides, plus 32 meters times 13.8, and we have 2 of those sides. So a total surface area of 2,042 kilonewtons. Times that by our 0.58 kPa, we have 1,185 kilonewtons. Let's add that all up. 1,774 plus 3,830 times 3 plus 376 plus 1,185. We get 14,825 kilonewtons. Now you'll see there's like a tiny small rounding difference again because the one that's posted used Excel. So if you're wondering why if you do these out by hand you get a slight difference, that's why. Now they told us to use 10% of the load as the earthquake load applied to the building. So 10% gravity dead equals 0.1 times 14,185 825. Or, well, that's actually a pretty easy one there, isn't it, Shannon? 1,482 kilonewtons. So, our base shear due to seismic is 1,482. I want to show you now, we're done with the math. I'm going to, hopefully this doesn't give anyone vertigo. Okay, so when we looked at that, it asked us to figure out the 10% load. This is the old school way. They used to do it in like pre-2000. Pretty handy method, pretty quick, and it's still a pretty good check if you know roughly what your area has for a percentage. It's gotten more complex than that because obviously you can imagine if it's about the soil moving around and the building on it, the type of soil could make a big difference. And the type of building could make a difference, how much the building moves, whether it absorbs energy, all of these things can change the value that you use. So this is the way we just did, and this is the number we just got. So pre-NBCC 97, somewhere around there. Seismic NBCC 2015, which is the way it would be designed right now, instead of this, well, actually, it was just one line here was the calculation. This was all just to calculate the dead loads, which we'd still need. We would pull seismic data from the climatic data, and then we would go through this calculation procedure, where this is about the fact that I got all of that information from the climatic data. This would be from a soils report. Now, I assumed site class C. Again, this is beyond what you would need to know, but this assumes it's pretty basic soil type. We often have D. And this is about the building. So these are all factors to do with the building itself. And then I have to calculate all of this. Here's a chart. Again, you don't need to know this. I just want you to see all of the things that go into calculating this. And it works out to be that the percentage I would actually be using with this refined approach is about 8.5% of the gravity load. So all of this to calculate this value right here, and if I calculated the base shear using 8.5%, it would be 1,262. So this is all just to say that the values come out still very similar. Often these new ones are slightly more conservative, but it allows us to refine our approach. You know, there's more science behind it. We're building better, more adaptable buildings, and so this is a very important part of it. And ductility, if you build in ductility, it's even more. It's not often what we do in Toronto, like I said before, but in places like Vancouver and kind of northern Quebec, it's a very big part of the design process. These values get put on a set of drawings. So here is a set of drawings that I produced a couple years ago. No, I guess it was about a year ago that went out. It's under construction right now. There's actually 2 buildings in the setup. So there's actually 2 parts to it, but you can see here that I actually write out what the base shear is and that seismic governance. So this is something that building departments look for. And there's other information in here that other scopes in the design would make use of as well. There was a lot to unpack in today's lecture. I do understand that. It's not going to be as hard as it sounds going forward. Next week, we're going to expand on the loads. Next week is a lot about bookkeeping. So kind of open up Excel, dust off your fingers. It's not going to be complicated, but it's really good for tracking things. The things you should know. You should understand the different gravity loads on a building. You should understand that there are different lateral loads on the building. You should understand, and this is important as an architect, which live load is applicable and if things are different than normal.
So you should understand the unusual loading conditions. And you should understand that wind has building, element, and external and internal loads that an engineer needs to think about. So internal partitions still have wind load on them. For studying, you should know the various live load types, and you should have access to that table for live loads. I will provide it in the exam, or I'll make an assembled document for that. Like, I'll pull out the pages out of the reams of pages you need, and to make one that's a handy, like, 12-page sheet that you can access quickly. You should know how to determine the dead load from assemblies. You're going to be doing this in structures too. This is a thing that's going to continue. You should know how to look up climatic data. You should know how to calculate snow load. Again, I've made it easy. I don't think I'm going to give you slopes. I might, but it would be very easy. No accumulated snow load. CB, you know, is 0.8. And you know that CW is going to be 1. Wind load, again, very easy. You should know how to calculate on the whole building, but I would never make you do that in an exam. Even in the assignment, I don't mark it. It's for participation. So, not even, because there's no real way to even know if you participated or not. But it's there for you to try out if you feel like really kind of getting your head around it. And you should know how to calculate quake from percentages. You don't have to do the full NBCC 2015 method. I'm not even teaching you that, but I showed it to you and talked about it so that you have it for a reference. So again, I know it was a lot. It was a long lecture. It was longer than I expected to record it as well. But this will be, in your whole, you'll end up having 24 lectures with me over 2 terms. There's maybe 2 that hit 3 hours, and this is probably the only one that goes over. If it does, it's broken up and chopped up for me, so I don't even know what the total is. So it's because we're able to kind of really dive into it. Next week, we'll expand on loads and talk about combining loads, how we figure out what the total loads are by applying our factors to it. So we're getting close to some answers. So I'll talk to you guys next week.